introduction to the Vasp. Okay, so actually the Vasp performs ab initio quantum mechanical molecular dynamics simulations, and it is based on the local density approximation with the free energy as a variational quantity and an exact evaluation of the instantaneous of electron ground states at each molecular dynamics time step. And the interaction between the ions and electrons is described by ultra-soft pseudopotentials or by the projective augmented wave method and a plane wave basis set. So it is based on the plane wave basis set, and these two kind of pseudopotentials, these two kind of bases is provided building the Vasp. And here is some highlights for the Vasp. So Vasp provides well-tested pseudopotentials for almost every element, those pseudopotentials is well-tested and has been applied to many cases. So it is somehow is valid, and the algorithms provided in the Vasp are efficient and stable. So it is very fast for Vasp to converge a calculation. And Vasp includes a 4-feature symmetry code which determines the symmetry of arbitrary conflictions automatically. So you don't have to assign the groups, the space group or the point group into the Vasp. You just give the Vasp the latest geometry, and it can identify the symmetry in it. And Vasp can conduct various calculations, for example, the density of states, total energy, band structure, and also the forces, and so on, many kind of calculations. And Vasp runs equally well on the superscalar processors, vector computers, and parallel computers.
What's a superscalar processor?
Actually, I have no idea about that, but it has listed on the manual of the Vasp. Yeah, and I think it has some brief, discussion about this part, but I didn't read too much about that. So here I listed. So actually, Vasp will use multiple input fires, and you just so based on these input fires, usually we just use these 4 input fires, and then based on these 4 input fires, you just use Vasp, and it will produce several output fires. So I will go into the mainly important fires one by one. So here I listed the main input fires. Usually you can't do the calculations with just these 4 input fires. So the first one is the most important input fire for the Vasp. It determines what to do and how to do, and contains a relatively large number of parameters. And the second one is Polkar. It contains the pseudopotential for each atomic spaces used in the calculation. And those pseudopotential is given by Vasp, and you have to choose the proper pseudopotential and combine them together. The third one is the postcard. It contains the latest geometry and ions positions. So it just identify the geometry of the latest. And the last one is K-points. It will create a K-point grid with K-point coordinates and weights or the mesh size. And you can also identify the high symmetry K-points in this file. So I will go through it one by one. So the first one is INCAR, and it has a bunch of parameters. It has a very large amount of parameters. So I just choose something that we were usually frequently used in our calculation. So first, usually we will define a system. Use system is equal to, for example, I use system is equal to silicon here as the notation of the system. So this is just a common line, it doesn't matter. Then we usually will use I start. So if it is 0, that means it will restart from the, it will not restart from the previous calculation, it just start from the initial guess. if it is 1, then it will restart from the previous calculation. And I charge, it provides initial guess for the charge density. If it is equal to 0, then it will calculate charge density from initial orbitals. If it is 2, it will take superposition of atomic charge densities. If it is 11, it will obtain the eigenvalues or the density of states for a given charge density read from the charge card. So usually we will use these two values. So actually it has also has a bunch of values for the I charge, and usually we will use these two, and this one is the fault. So usually if we just do the self-consistent calculation from the very beginning, then we will use I start as 0 and I charge as 2. And then if we want to calculate the band structure of the eigenvalues or the density of states from our self-consistent results, then we will use I start as 1 and I charge as 11. And we have please note that it will do the non-self-consistent calculation. So if you have set some parameters for the self-consistent calculation, in this case it will give you some errors. And another one is energy cut. It is the cut of the energy for the plane wave basis set in the E-volt. So usually this number will be given in the pseudopotential file. So Vasp can directly read the energy cut from the pseudopotential file, but it is better you set it by yourself manually so that you can control all of this.
So just to remind you, right, if you didn't have a pseudopotential, you could make these plane waves arbitrarily exact by just increasing the plane wave cutoff. It's a little bit more complicated when you have a pseudopotential, but basically the higher your cutoff, the better your basis set conversions, right?
Yes.
You know, the more precise your results become. So you have to always be a little bit aware that, you know, your results may be converged only modulo the energy cutoff that you're using.
Yeah, and sometimes we'll try to find the optimal energy cut by calculating by doing the self-consistent calculation with different E-cuts, and then you find which one. So when you find the difference of the energy is very minimum, it's minimum to ignore, then you can just set the energy cut at that level and do the following calculations. And I smear and sigma, it is parameter for the smearing. So I smear identify what type of the smearing it does. So usually we will use -1 Fermi Dirac smearing, 0 Gaussian smearing, and -5 the tetrahedron method with block corrections. Yeah. Theoretically, we can do all the calculations with I smear with 0, but in some cases, for example, if we want to do the semiconductor or the insulator or something, that we will use -5 here.
So Runxue, can you remind us a little bit what smearing means in this context?
Sorry, what?
What is it good for? Why should I care?
Oh yeah, so it will be good to do when we do the metal calculation. Yeah, so it is kind of to increase or reduce the resolution of your calculation near the Fermi energy. Yeah, but here actually in the Vasp, it will always use the smearing. So it just what type of smearing you're using. So usually we will use 0, and also we have to set sigma. It will determine the width of the smearing in E-volt for the finite temperature LDA. And usually for this sigma, we will also try for, if we want to find an optimal sigma. So usually we will just set 0.1 or 0.1 or 0.2. That's okay, but if you want to find the optimal sigma, then you can do the calculations with different sigma and find which one has the lowest entropy T times S. Yeah, it was shown in our car. I will go to it later. Oh, by the way, so if we're doing the band structure calculation, we were using a line mode of the K points, which I will go through it later. So here you cannot use this one because if you want to use the tetrahedron method, you will have to have a tetrahedron mesh grade. And later, this is I-spin. It would identify if we will have spin polarized or non-spin polarized. And the magnetic moment, it specifies the initial magnetic moment for each item. And the energy difference, it defines the accuracy for the electronic minimization. So if your energy difference is below the number you have set here, then the calculation will stop. And the precision, sorry, I forgot to add the description of it. It just gives the precision of the whole calculation. You can use, for example, high, low, normal, something like that, or automatic. Another one is NELM. So it is the maximum number of the electronic self-consistency steps. So if the energy hasn't reached for the energy difference, then it will do this number of the steps in your calculation. Yeah, and actually we will also have another parameter as NSM. It will be the maximum number of the iron relaxation steps. Yeah, I will show it in the examples, I think. And then we will have a bunch of parameters for the charge density mixture. So the first two are the tags for the mixture, and it will be a detailed description in the manual. But I think the most important one is this L max mix. It identifies which L quantum number pass through the mixture. For
what
SMP,
is a mixer?
So it's just a it's kind of mixing methods for the charge density.
So what does that mean? Like for initial gas, or?
Is that as you're iterating, there's some damping in the density matrix, or?
Yeah, I think it will. Yeah, it's kind of some damping. Yeah.
And so these parameters say that you're only damping S and P, or you're damping S and P and D, or is that what's happening here?
I'm not quite sure, but I think.
All right. So another question. You say L quantum numbers, and that makes a lot of sense for an atomic basis set, a Gaussian basis set. But this is a plane wave code.
Yeah, but it will have the projection to the atomic orbitals. Yeah, so actually it is not exactly, so I believe that in the code it is not exactly deal with the atomic orbitals, but it is suggested that if you set, for example, if you have the F electrons, you can set these parameters to 6, and it will give you a better results or a more reasonable results.
Okay.
Yeah, and the orbit parameter, it will create the output files at certain level. So usually we will use this one for the band structure. For the PAW method, for example, the PV, and it will produce those cards. This will give us the density of states, and the pro card, I will go it later. And also you can determine how the ions are updated and moved. So it determines what kind of algorithm you will use.
So this is for dynamics, and if we're just doing structure, we shouldn't care about this, right?
I think this one you should care about this.
So if I fix my geometry, and I just want to have a result for a fixed geometry, do I need to have this thing?
I think I think in the VASP it will also, so during the self consistency it will also do the relaxation for the irons.
But I must be able to switch that off so that I can get, you know, a result for a fixed structure where I just keep my iron
Oh
fixed.
yeah.
No?
I mean, there should be an option like you can relax the
Yes.
geometry, but
Yeah.
you should
that-
never like doing it like automatically.
Oh
Yeah,
yeah,
it
yeah,
should never
yeah.
be the
Yeah,
default.
yeah. This one you can just turn it down. Yeah, but sometimes if you just give it a rough parameters initially, then you can calculate the latest geometry at the end of the calculation. Yeah, you can just turn it down.
But,
Oh, sorry, go.
sorry, but you say at the end of calculation, but that's not good. If you want to optimize the geometry, you do it during the self-consistent. You try to minimize the energy. It's not like a post-processing.
Let's skip this. I think this is a distraction here. And, you know, for the typical cases that we're interested in, we don't need to pair.
Okay, and then the second file is the pole car. So it will contain the pseudo-potential you will use for the calculation, and make sure that the ordering in the pole car corresponds to the spaces ordering in the postcard and in-card. And postcard files contains information about the atoms and the Ford's energy cutoff. And we have multiple kind of pseudopotentials. So if we divide it by methods, we have the ultra-soft pseudopotential and the projected augment wave. And if we divide them into different exchange correlation function, then it will have LDA and GGA. And GGA also have PW91 and PBE, these two types. And if we consider the semi-core states, then we have the elements and element underscore SB, which will have the semi-core states at the valence bases, and at electron underscore PV with P semi-core states at the valence bases, and elements underscore D with, sorry, I write it wrong, so it is with D semi-core states. And for the maximum energy, it will also have the element underscore H, which will have a harder pseudopotential. So usually we will use PAW, PAW for the transition metal 3D elements, lanthanide and actinide. And for the 3D elements, it is recommended to use this underscore PV. It is from the experience. So.
Actually, so what does that mean, harder superpotential?
So that means it is very hard to cut it.
What does that mean?
Yeah, so for example, if you have the CO, carbon oxide, then it will have a very strong bonds between them, and you will use the hard superpotential here. But if we just if we are considering the latest, we almost never use this.
Oh, okay. Also, I guess also you mean hard to cut probably also because for the semi-core electrons, you cannot have a clear separation between core and valence.
Yeah, that's true.
So that's typically one of the uncertainty.
Yeah, so it's kind of the bonds between the elements are very strong.
So typically when superpotential include the semi-cores, that will or either included or excluded, and then we need some extra correction. So.
Right. I guess if we want to know more about this, where would we go and read up on it?
You can just go to the manual of the VASP. I will list it at the end of the reference.
But your sort of experience is that, you know, if we just want to do something, we do, you know, we find the pseudopotential for the method we want to use, for example, PDE. So we go find the exchange correlation for PDE, and then what we.
Yeah. So actually, for large large core elements, I think usually they only have this one, and for the transition metal elements, maybe they will have the three. I seldom find this one. Yeah.
So which one is your go-to one? P X, XSV, or XPV?
They will have both, and you can choose one. For 3D elements, usually we will take this, and if I remember right, for the 4D elements, usually it is not so good, and people will use this one or this one. And for 5D, it also the choice between this one and this one.
And so we just try both, and we see what.
Yeah. So you just do the calculation and see the the outputs.
Okay.
Yeah, so, and the third file is the postcard. It determines the latest geometry. So the first line is a common line, and then you can give the universal scaling factor, which also we will put the latest constant here. So if you have if you are in the cubic, then you can put the latest constant here. And then the three lines gives us three lattice vectors defining the unit cell of the system. And then we will specify the number of atoms per atomic spaces. For example, if I have neodymium nickel oxide, then I have one neodymium, one nickel, and two oxygen. And ordering must be consistent with the POCAR and INCAR. And then this line determine whether the atomic positions are provided in the Cartesian coordinates or in direct coordinates. So if the first character is C or K, it will switch to Cartesian mode. And for anything other here, it will do in the direct coordinates. And then it will give the three coordinates for each atom, one by one. And with the ordering that you have listed here.
So you have the formulas for direct and Cartesian. And Cartesian has a little s. Is this your overall scaling factor?
Yeah, it is kind of the scaling factor here. So you can do, as what I have understand from the manual, you can do any scaling here.
Sure. And so why is there no scaling factor in the direct?
Yeah, because you have identified the latest vector here, and then this is your atom position, and this one should be exactly your atom position, and this will be x1, x2, x3. Yeah, and your A1, A2, A3 has been defined here.
Okay.
And the fourth file is the K points. So it will determine what kind of K points you will use. Usually we will use two kind of formats here. So the first one is automatic K mesh generation. So this is a common line, and you put 0 here. 0 means that we're using the automatic generation scheme. And we have three formats. The first one is the automatic format. It will fully automatic with the length L. So you can see it here. Yeah, so it will generate NE, N2, N3 at this and do the K mesh here. And another one is the gamma centered or the Mohorst pack case. So this one is the formula for the gamma centered K mesh, and this one is for the Mohorst pack case. And then you can label it here, and this line means the large N1, N2, N3, and this line means S1, S2, S3. The shift of your the shift of your position.
So wait a minute. So Monkrospock grids can either be gamma-centered or not gamma-centered.
Yes.
And so the gamma-centered grid is also Monkrospock, or that's something special?
They are not exactly the same, but they are very similar to each other. Yeah. So it's kind of that Monkrospock pack will have shapes based on the gamma center.
So okay. So I think I know what's going on, but if you read the original paper of Monkros and Puck, right, they actually have both grids that are gamma centered and grids that are not.
Yeah. So actually they are the same. But Vasp has defined different formulas for that, and there's only the shifts between them, but they are the same. So you define the same parameters here.
So wait a minute. So if I want a gamma-centric grid, what do I do?
Yeah, so this line defines the big N1, N2, N3.
Right.
And this line defines S1, S2, S3.
And so if I want to have the non-gamma-centric grid, what do I do?
You can do you can use the third one. It will be if you don't want to, if you just want to have a shift.
The question is how in the parameter I choose the first line or the second line.
Yes.
Oh yeah, this one.
So if
So
I
if
write
you
Monkrospock,
put gamma here, if you
oh,
put
I have to write
anything
gamma there.
have G here, then you can do the first one. And if you have anything with M, and then you can do the second one.
I see. Okay. So basically, I just change that first line and I'll switch it from one to the other. Okay.
Yeah.
Good.
And the third one is the list frequently used. So it will just so I think it will just explicitly shows the Cartesian coordinates for K points.
So what do you usually use?
This one.
Monkrospock, not
Or the
gamma-centered?
gamma-centered. This
Okay.
one.
Yeah.
Yeah, and another one is the strings for the K points for the band structure calculation. So this one is for the band structure calculation, and we will call it as line mode. So you have to write line mode here, and this means the number of the K points. This is a common line; it doesn't matter. This is the number of the K points, and you have to identify it as line mode here. And you can, in the line mode, you can use direct or the reciprocal coordinates here. And then you have to define the path here. But you have to define, for example, if you want to go to gamma x, w gamma, then you have to give gamma to x the first pass, and x to w the second pass, and w to gamma the third pass.
So what if someone doesn't know what is that? I mean, so
But you have the coordinates there, right?
Yeah, so you have to
need
check
know
the
coordinate yourself.
yes. So
Yeah.
then you have to check any textbook that has the high symmetry K points coordinates there. Yeah, it just use the the most common used one, the coordinates. Actually, you define it directly. This is just a comment. So when we define those four input files, then we can have multiple output files. So here I just listed the main output files that we are most interested in. The first one is the outcar. It will contain most of the results and the information for each iteration. And the second one is charge car. It contains the so basically it just contains the charge density and also other information related to that. And the third one is dot car. It contains the density of states, and the eigenvalue contains the quotient eigenvalues for all K points. And pro car, it will contain the the opto and side projected wave function corrector for H band. So for outcar, it will have a very large file and a bunch of information in it. And the most frequently used information here I have listed here. So you can check the volume of system by grab the volume. And you can check the total energy of the system by grab the total energy. And the Fermi energy, you can grab Fermi in outcar. And for the reciprocal lattice vectors, you have to use VI and search in the VI mode, then search for reciprocal lattice vectors. And also the difference between the free energy and the total energy, which is T times S. You can grab the energy entropy in the outcar. And usually we will use this one to determine which sigma we will use, which I have.
So Runxue, this is DFT. DFT is a ground state method.
Yeah.
So entropy shouldn't be that big, right?
Yes.
So what does it even mean to have an entropy?
Yeah. So I remember that usually these two numbers will be the same. Yeah, but Vasp also can do dynamics, not the status calculation. It can do the dynamic calculation, and they may have different different values between them.
So,
I'm confused, but that's probably a side point. But basically, I should expect energy and free energy to be the same.
Yeah, usually it will be the same if you do the
yeah.
stat.
So another question, right? So somebody has run Vasp, and gives me a Vasp output, and so now I look at this outcar and I want to see if there's if that simulation was okay or not. What are sort of your first go-to places to look whether that was okay?
Yeah, so usually we will see if we have the the optimal the latest geometry that you are expected. And
so that would mean that Vasp actually did a structure relaxation, and I look at the output.
Yeah, so
structure
usually
again.
we will do this one.
Okay.
Yeah, but so it will not change your latest geometry so dramatically, but you can see if yeah, so if the number is reasonable, then your calculation is somehow reasonable.
So in other codes, you would typically just follow the energy and see that the energy converges to something sensible.
Yes.
But are there other indicators that you're looking at?
Sorry, let me think about that. So,
or do they treat anything other than energy difference?
yeah, it will have the energy difference.
No, anything other than.
It actually it has many things output in this output files.
So yeah, and that's usually the problem, right? The output files are so overwhelming that you really have to know what to look for to see whether this worked or not.
Yeah.
And so you look at structure, and so I would typically look at energy. But what are other things that you would go look for?
I think that's the two typical things that we will check for that.
Okay.
Yeah, and then maybe we will use we will just check for the the later results, for example, the band structure or density of states.
So you would actually then go and look at the final band structure and density of states and compare it to something that you know from somewhere else or that you expect or whatever.
Yeah, usually I will do that.
But if the density of states is in a way already a very processed output.
Yeah.
Right. So at that point, you don't you usually look at the density of states as a function of iteration that you see sort of how it's converging, or like.
No,
How-
just the final one.
Just the final one. And then how do you know that the final one is a good one?
You can compare it to the literature.
Yeah, what if you're the first one running it? You know,
Um,
what if you're the guy running a paper originally?
Yeah, that may be compared to the experiments. Yeah, so,
But it must be that the calculation somehow tells you that, yes, this is now a result that is, you know, fully convergent, trustworthy within the DFT approximation.
I will check it later, but so from my experience, I will only check the latest geometry, total NG, Fermi NG.
All right, fair enough.
But so,
Yeah, and you can check if it is convergent or not. Yeah, but I think this
But I mean,
is
if
at
it's
the
not
very
converging, then you shouldn't look at anything,
Yeah.
right? I mean, it makes no sense.
so two comments. The difference between free energy and total energy that come from the smearing. So in the smearing, on one side you have this Fermi Dirac distribution. So more than
Fermi smearing, yes,
Yeah.
but she had all sorts of other smearings too. But okay, so
yes, so if you're using this Fermi Dirac smearing, then you have this broadening in a way that well, I guess someone will consider this as a finite signature LDA. So that's where the difference between this free energy and total energy comes from.
so if I have an insulator, I would expect 0 there. Yeah.
Well, I guess even with the insulator, you just still use the Fermi Dirac smearing, you
Yeah.
still have the difference. So if you don't, I imagine if you don't use that smearing, this will be exactly the same. The other thing is the geometry optimization. If you want to have a quantitative comparison, you should probably disable it because that actually makes difference.
Yeah, you can disable it.
Yeah, just like it's not like people will typically do when they do this calculation.
Yeah, but yeah, you can do it later if you confirm that your other parameters are valid. I mean that you can do the self calculation first with the iron relaxation, and you can check if your other parameters are good. Then you can shut it down.
All right, good. Yeah, let's move on.
Yeah, and then and another one is charge card. So it can use as output and also an input file. So first it determines the latest parameters, the same as the postcard. And the most important that it will give us the number of x, the number of the points along the x, y, and z. So usually, so this one will be generated from the self-consistent calculation, and then we will do the band structure calculation based on that. So sometimes the VASP will not give the same of these numbers for the non-self-consistency calculation. Then you have to set it manually, as what you have got in the charge card. And then the density of states and the eigenvalue. So here I just show the eigenvalue part here. And the most important thing is around here. So this is the band number, the ng for the spin up, ng for the spin down, and the occupation number for spin up and occupation number for spin down. And this is the K points this is K points and a bunch of the band structure. And the contribution of this K point. I didn't remember it clearly, but usually we will not use it. And so based on the eigenvalue files, we can plot the band structure. And sometimes if we want to have the atomic orbital projected band structure, then we have to have a look at the project card here. Yeah, so the most important part is also here. So here we're listed as band 1, band 2, and band 3. And it will give you the entry of this band and the occupation number for this band. And then it will gives you each atom projected and orbital projected for the contribution for this band. Yeah, so for example, we have neodymium, nickel, oxygen, oxygen. So the nickel PY will gives the band 1 as 0.508 contribution here. And then based on that, you can plot the orbital projected and atom projected band structure. And there is another used for technique. It's called plot for Vasp. It will directly give you the density of state and the band structure from this kind of software or the code. Yeah, you can just use. So in the output files, we will have a file called vasprun.xml, and plot for Vasp will directly read this file, and this file contains all the information that you have input and also generated from the Vasp calculation. And then it has the interface address. You start the plot for Vasp, and you can select the electronic or the density of state and bands, and then you click show, and you can show the bands, show the density of states, show the bands and density of states, and other options. Then you can. So this one will gives you if you want to just quickly check the density of state and the band structure, and you do not want to, deal with the data I have shown you before, then you can just use this one. But if you want to have a very beautiful plot, then you have to plot it by yourself. Then I will give you some examples. So the first example is for the silicon, and the postcard will give you the geometry of the silicon. It is just FCC, and we use PVE potential for the silicon, and if we want to have the band structure, usually we will do two-step calculation. The first one is self-consistency calculation. So we will start from the initial gas, and the I charge will be 2. And actually this one is provided in the pseudo-potential, where you can manually set it here. And I smear is 0, and you can use also have -5 here because it is semiconductor M.1. And we will use the Marquardt pack mesh here, and it is 11 by 11 by 11. And after that, we will have a bunch of output files, and when we go to this non-self-consistency calculation for band structure, we will have to copy the charge car file into this calculation, and we'll also build the same postcard and polcar, and we will modify the in-car here. So first we want to have the density of state and the procar file here, and the I chart will be 11 so that it can read from the charge car file. And since this is non-self-consistency, we can only have So since we have line mode k points here, we can only have I smear as 0. We cannot have I smear as -5, but we can have I smear with other kind of smearing. And then we will give the reciprocal coordinates for the silicon. Then this is band structure from the Vasp. Another example is for the nickel oxide. So it follows the same construction here. So since the nickel oxide is antiferromagnetic, so it will have a kind of supercell there. And so why we have 2 and 2 here is because we have 2 different nickel. Sorry, we have, so never mind. So yeah, we have 2 nickel and 2 oxygen. Why we want 2 nickel and 2 oxygen? Because we have 2 different nickel in our unit cell, and we will construct the supercell shown here. And then for this part, we will use nickel. The magnetic moment for nickel is 2 mu B, and oxygen is 0. So it will be 2 minus 2. So first nickel, alpha nickel, beta nickel, and 0, 0 for oxygen.
Runxue,
Sorry, go ahead.
how does your code now know that this is nickel oxide and not manganese oxide or so? Where's nickel?
Oh, so you will have to contain the postcard.
So this is only in that postcard, in the pseudopotential.
Yeah, pseudopotential.
And so there I say nickel, nickel, oxygen, oxygen.
Yeah.
And that's how it knows about atoms.
Yeah, so for postcard you only have to contain nickel and oxygen, and that's it.
So does the system equally the outside mean everything? Like the actually?
Sorry. So actually in your postcard you will have the pseudopotential for nickel and for oxygen. So that means here this one is nickel, this one is oxygen.
Okay.
Yeah, and this is 2 nickel, 2 oxygen.
I see. So there's like, these things are all sort of interconnected.
Yes.
Alright, go ahead, sorry.
Yeah, and we do 4x4x4 calculation here. And after the self-consistency calculation, then we do the calculation for band structure. Also, the only thing that we have to modify is some things here and here I have mentioned before. Yeah, and sorry, I also have the band structure for the crystal, but you can see the black line. This is from the Vasp. And the final example is for the neodymium nickel dioxide. So
now, can you go one back? Yeah, see, if we look at your postcard, you have your unit cell coordinates, and then you have 2 and 2. And now if you go back to your neodymium nickelate,
yeah, actually you can, so it will be recognized as a common line in the Vasp. You can contain it, you cannot.
okay, so this is just a sort of a comment
Common
for
line.
yourself, and what really matters is how you put the postcard in there.
Yeah, so usually we don't contain this line, but if you are not quite sure what you're typed in, you can just add that line.
Alright. And so your postcard that you have there, are these 3 lines, or are you
Yes.
actually?
Oh no, so actually the Vasp will provide a postcard, the postcard files for each elements. Then you have to copy them into one files,
Right,
and
so
in
that's what I
ordering of
remember.
this.
And you have to copy them in the right order.
Yes.
So you go to the Vasp provided zip file, you find the pseudopotential you want,
Yeah.
you copy it, and you paste
Put
it in
it
into
in
your
postcard.
postcard.
Yes. Yeah, nothing special here. The only thing that I'd like to mention is, so here, this is the number of the iron relaxation step. So if you are doing the band structure, since this is non-self-consistent, you have to set it at 0, and nothing else special here.
And if I want to have this for a fixed geometry that I specify, I guess I can already set to 0 here. Is that correct?
Yes, and the default value for this is 0.
Okay.
I have a question. So what does this make for neodymium is 0.6?
Yeah.
So
That,
You can actually
then
express
nickel is 5 and oxygen 1.0, oxygen 2.0.
So it doesn't have to be integer.
Oh yeah, it doesn't have to be integer.
And why are these good values for the magnetic moment?
Yeah, actually I just use the magnetic moment I found in the literature.
What type of magnetic moments are these?
It's just the magnetic moment for each element.
Like out of atomic physics measurements?
Sorry, what?
Like if I have an isolated neodymium atom or so, and I mean, what I measure its magnetic moment?
No, I think this is magnetic moment in this compound.
So if I get this wrong, right? If I don't know what the magnetic moment of neodymium should be,
Yeah, you can remove that one.
what? And during the cell consistency, it should be adjusted, right?
Yeah.
It may be a bad starting point, and maybe it converts to something different. So,
Yes, it can be. It can convert to something.
so at the end, do you get updated magnetic moments that you can look at?
Actually, I haven't checked this for this.
And does this choice influence anything?
Actually, from my experience, at least for this compound, it doesn't affect a lot, because previously I also have tried for 000. I didn't add this line, and it is almost the same. Yeah, but I think for example, for the antiferromagnetic moments, antiferromagnetic nickel oxide I have mentioned before, this one maybe matter. Yeah, and this is just the band structure here, and I have also shown you the opto-projected contribution on each band.
So how do you get these orbital projected contributions?
I have mentioned here. So for each band, it has listed the contribution for each atom and each orbital.
All right. So what you're showing us here for the other band structure plot, the one that you just had, right? That's not from any. No, sorry, the one that you just, yeah, this one. That's not from any Vasp visualization program. That is something that you got from the script that you wrote yourself.
Yes. I don't think Vasp can do it directly. Yeah, because Vasp cannot produce any plot in itself.
Right.
Yeah, so the plot for Vasp is also, other one has built it, a kind of post-analysis for the Vasp. And the plot is very, ugly from that. So, so I think usually we will just write some scripts to plot this band structure. It is not too hard, because you just, analyze the data. And the most important references for the Vasp is the Vasp guide I have mentioned as manual during my talk. And another one is the Vasp wiki. They have the wiki online, and you can check. There were also many examples there, and you can check for that.
All right. Thanks.